Hi there! Welcome to Vector Mechanics for Engineers Dynamics, 11th edition of Beer and Johnston, Cornwell, Self, and Sanghi. I am Joshua Emmanuel Pagulong and I am going to present to you this video in solving about a problem in this book. Again, welcome and thank you for checking this video. This video will basically present a solution to a specific problem in system of particles. I hope you'll enjoy. System of particles is located in the chapter 14 of this book. This is a presentation of solution of problem, specifically number 14.24, as a requirement in the course of ES12 and the Chemical Engineering students of University of the Philippines, Visayas. Now let me present to you the flow of this video. First is the introduction, and I will present also the concepts involved, and I will present to you the problem, which is 14.24, and illustrate the problem, of course solve the problem, and finally show you the results of our solution. This chapter dealt with the motion of system of particles, where the motion of a large number of particles is considered together rather than separately. In this first chapter, we already learned that how to compute the linear momentum and the angular momentum of a system of particles. We defined that the linear momentum L of a system of particles is the sum of the linear momenta of particles, and we defined also the angular momentum HO of the system as the sum of the angular momenta of the particles about O. So as you can see in here, the equation is about on the summation of each of the particles. So you will be asked to solve several problems of practical interest, either by observing the linear momentum of system of particles is conserved or by considering the motion of the mass centers of the system of particles. This video is focusing more on the motion of the mass center of a system of particles. The mass center of system of particles move as if the entire mass of system and all the external forces are concentrated at that point. So the problem that I will be discussing later on is the case where a body exploding while in motion. It follows that the mass center of the resulting fragments move as the body itself would have moved if the explosion had not occurred. You can solve this type of problems by writing the equation of motion of the mass center of the system in vector form and expressing the position vector of the mass center in terms of the position vectors of the various fragments. And then you can write the vector equation as 2 or 3 scalar equations, and finally we can solve the equations for an equivalent number of unknowns. Now let me present to you the problem 14.24. A 6 kg shell moving with a velocity VO 12 meters per second I, negative 9 meters per second J, minus 360 meters per second K, explodes at point D into 3 fragments, A, B, and C of mass respectively 3 kilograms, 2 kilograms, and 1 kilogram. Knowing that the fragments hit the vertical wall at the points indicated, determine the speed of each fragment immediately after the explosion. Assume that the elevated changes due to gravity may be neglected. Now let me present to you the illustration of our problem. We have our wall and we have our reference axis, the X, Y, and Z. We have their point D, wherein that point is where the shell will explode. So now here's the illustration. As we can see, the shell is moving, so it has an initial velocity, and when it began to explode, the fragments are split into 3, and the 3 fragments are located at 3 different points of our wall, so as we can see in here in our figure. Now let me present you the dimensions and the masses of each fragments. Particle A is located 1.5 meters away from the origin in the negative x-axis, so as you can see in the figure. So it is located here. Now the next is particle B. It is located here, which has a mass of 2 kilograms, 4 meters away to the positive x-axis and 2 meters above the y-axis. And our last particle C is here, and it is located 3 meters below from our origin. Now this point is where the point D, wherein the shell exploded. It is 4 meters away in the z-axis. So the shell's initial mass of 6 kilograms, it is given in the problem. Now in order to solve the problem, we must know what are the givens. So we know that the shell has an initial velocity, and also it has a total mass of 6 kilograms. The fragment position coordinates are also indicated in our illustration, and the fragment mass, we know that A has a weight of 3 kilograms, B has a weight of 2 kilograms, and C has a weight of 1 kilogram. Now, it is also given that we have a constant velocity, and since it is an explosion, we know now that it is a system of particles, and now since also an explosion is case 1, and also we can finally then say that we can use the equation for the conservation of momentum. So what is required in the problem is that we need to identify the speed of each fragment immediately after the explosion. Now for the solution part, first we must obtain the values of the position vectors of each fragments RA with respect to D, which is the point where the shell began to explode. Position vector of fragment B with respect to the point D, and also where the shell exploded, so as for our CD. After getting the position vectors of each fragments, we need now to get the unit vectors. So by obtaining the unit vectors, we only need to divide our position vectors divided by the magnitude of each position vectors. Now after that, we can now solve the problem by using the conservation of momentum equation, which is indicated here, since we know that linear momentum is equal to the summation of all the mass times v of the fragments. So we can now use this equation. Now after, we need to resolve our equation into components separately, component I, J, and K. So now let's start. First is to identify the position vector. So now we have known that particle D is located somewhere here, and it has a position vector for K. Now the next particle A is located here. Now we can say that it has a position vector here, and now in order to get the position vector of A with respect to D, we just only need to subtract the RA minus RD, which is here. So negative 1.5i minus 4k value for RD. So now we have our RAD. Now since we need the magnitude of RAD in order to obtain our unit vector later on, we need to get this magnitude. So this magnitude is obtained by the square root of the square of 1.5 and the square of 4. So we already know that in our basic physics. So as we solve the particle A, so as the process is the same for particle B, we just need to also obtain the magnitude, and also for C. Now next, since our next goal is to obtain the unit vector, so in order to obtain the unit vectors, we need to divide our position vectors RAD divided by the magnitude of RAD. So now we can easily substitute that here. Now our next process is, since we assume that the elevation changes due to gravity is neglected, then we can say that the velocity vectors after explosion have the directions of the unit vectors. So now we have this VC, VB, and VA in this in the left hand side are the velocities of the fragments after the explosion. Now, by knowing that, now we can now get the velocity of each particles by using the equation of the conservation of momentum. So we know that particle A, the shell has a initial mass of 6 kilograms, and it is also given that we have this initial velocity 12i minus 9j minus 360k. Now next is to identify the momentum of particle A, mass times VA. So we have a mass of 3 kilograms, and we have solved earlier that VA is equal to this 4.272 times negative 1.5i minus 4k. So this is the unit vector, and this is the VA. So now the same for VB, the momentum for particle B, it has a mass of 2 kilograms. And next for C, it is a mass of 1 kilogram. Now using that values, we can now obtain this long equation here. Now after that, we just need to simplify these equations and separate them by components. As you can see in here, it's separated by components I, J, and K. Now using that simplified equation, we can now separate them by components: component I, component J, and component K. So component I, this part here, is now equated to this part and this I here. So we can obtain here these equations. So next, in order to solve the velocity of each fragments, first we must set that the component I is the equation 1. So by the way, we will solve this 3 equations by substitution. So now we just transpose the value of VB on the other side, so we can obtain the value of VA. The same for equation 2. From component J equation, we can obtain the value of VC and VB on the other side. So now we only need to substitute these values VA and VC to our component K equation here. We set our component K equation as equation 3. Now substituting this VA and VC here and here, now we can solve for the value of VB. Now we already have this 394.59 meters per second. So this particle here has a velocity of 394.59 after the explosion. Now next, in order to solve for the velocity of this particle A and C, we only need to substitute the obtained value of VB to our previous equations. So for equation 1, we can now use this. So substitute this is VB. Now we already now have the value of VA, which is 431.14. Then after is in order to obtain the value of VC, velocity of this particle. Now we already had the value of VB, so we can now obtain the value of VC, which is 528.65 meters per second. So now we have these values of all the velocity. So now for our final answer, for VA is 431.14 meters per second, for VB 394.59 meters per second, for VC 528.65 meters per second. So these are the speed of each fragment immediately after the explosion. So that's it for the problem. So just a quick recap in order to share to you the key points in order to solve the problem. So first, we need to read and illustrate, analyze the problem. Would have become handy if you have able to illustrate and give the involved factors that contribute to the problem. Look for significant equations, kinematic equations, linear momentum, angular momentum, impulse and momentum equations, collision equations, and many more. So since that we know this equations that we can use, we need to apply our data the given data in order to obtain the required data using the principles that could be applied depending on the problem. Now we need to evaluate our final answer, verify or check if possible, and generate conclusions based on the factual data obtained by the solution. So that's it for this video. Thank you for watching. And again, I'm Joshua Pagulong, and the book that I use for reference is the Vector Mechanics for Engineers Dynamics, 11th edition of the Beer and Johnson.